So let's see, what would our degree of our polynomial be? Well, I have an x squared, and x squared is x to the fourth, right? X squared times x squared is x to the fourth, then times x would be x to the fifth. So my degree should be degree 5. So I'm going to solve this. So I've got three things multiplied together. So x minus 6 equals 0. X squared minus 4 equals 0. And x squared plus 9 equals 0. That's 6. Add 4. Subtract 9. And x equals 6. X squared equals 4. And x squared equals negative 9. Square root. So I'm going to get x is going to equal 6, negative 2, and positive 2 for the square root of 4, right? And then for the square root of negative 9, that's going to be negative 3i and positive 3i. Remember, if I have a negative inside the square root, it comes out as an i. So I've got negative 3i and positive 3i. So that should be 5 answers. 1, 2, 3, 4, 5. There we go. All my roots are right there. These two are imaginary. So they're not really roots that you'll see on the graph. But we're going to talk about those today and what they kind of look like. All right, next one. Let's see. What is in 3, 4, 5, 6? So I've got x times x squared times x cubed, right, is x to the 6. So n is 6. So I've got 2x minus 3 equals 0. X squared plus 8 and x cubed minus 8 equals 0. I forgot to put equals 0. Marco and Melanie. Okay, so add 3, subtract 8, add 8. I've got 2x equals 3. X squared equals negative 8, and x cubed equals 8. Square root, cubed root. Oh, so x is going to equal 3 halves. Let's see, 8 is 4 times 2, so that's going to be 2i root 2, or negative 2i root 2. And then the square root of 8, the cubed root of 8 is just 2. And then there's a couple more imaginary ones, or complex roots. And then there's 2 complex roots that we don't know because we have a cube root. So 1 real, 2 complex roots. And that should give me 6. 1, 2, 3, 4, 5, 6. Yep, there's 6. And of course we have our 2 imaginary roots. Okay. Beautiful. Okay, so now we're going to talk about basically, we broke the graphing of polynomial functions into 2 pieces. So today we're going to talk about what it looks like and what like the degree means on what it looks like if the degree is even or odd, if my coefficient is negative or positive, what happens. Remember we talked about a couple days ago, if I had a multiplicity, right? If I had a root that had more than one in the same place, what happens to my graph if it looks like that? So we're going to talk about really the functionality. Okay, so what are the key characteristics of polynomial graphs? So we're going to talk about that. The first thing we're going to talk about is the shape and the end behavior of polynomial graphs. The graph of a polynomial function is smooth. There's no gaps, sharp corners, or cusps. So when I'm drawing them, or when we're sketching them, because we're not actually going to graph them, we're just going to sketch them. We want to make sure that it's hard. Trust me, I know sometimes they get kind of sharp. to not do a V, but we want to make sure that they're kind of looking like mountains or molehills, so they're curved instead of points, not mountains. So make them curved, okay? So we want to make sure that they look like this. Okay. So we're going to talk about if I have an even degree. So if my degree is 2, 4, 6, 8, ... right? So no odd degrees. What does my graph look like? Well, we know if it's even, if it's a second degree, I guess we're going to talk about also if the leading coefficient. So if I have, let's see, let's just say x squared or x to the fourth, right? So it's positive. I have a positive leading coefficient. So the leading coefficient's the number with the variable, right? So I have 2x squared, blah, 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 blah. Doesn't matter what's after it. And it doesn't matter if it's even or odd. I could have 5x to the 6th minus 4x to the 4th plus 3x minus 1. Okay, it doesn't matter what comes after it. It doesn't matter. The only thing that matters is that this number is positive and this number is even. So my degree is even and my leading coefficient is positive. That's what we're talking about, okay? So we know that if it's a squared, x squared, it's a parabola, right? Okay? What happens at the end of it? Well, both my ends are pointing up. So if it's positive, it's an even degree, okay? And if it's even degree and both ends, and it's a positive leading coefficient, my ends, what's happening at the end, or the end behavior, is my ends are pointing up, okay? Look at this. Doesn't matter. Look at all these graphs. What's happening to all of them? Okay? Look at the ends of all of these graphs. It doesn't matter what's happening. Look at this big one. What's happening in between? What's happening at the end of all of the graphs? Okay? So I want you to just take a second and write down what you see with all of this. And I already talked about it, right? But what's happening with all of the graphs? If I look at just the end pieces of it, what's happening to all the graphs? And we have to remember if it's an even degree, so it's 2, 4, 6, 8, and my leading coefficient's positive, what do they all have in common? Okay? Well, what they all have in common is my ends are all going in the same direction. If it's an even even degree, they're all going in the same direction. If it's positive, they're going up. And if it's negative, guess what's happening? If my leading coefficient's negative, guess what's going to happen? They're both going to go down. Okay, so that's what we're going to talk about next. So if I have, remember this is still an even degree. Even degree. Now look at my endpoints. I still have an even degree, so x squared, x to the fourth, 3x squared plus 6x minus 10, doesn't matter. Okay, what's happening here? Oh, here, now my leading coefficient is negative. So all these leading coefficients go to negative. Now the only thing that changed is my ends. What's happening at the end of my graph is now my ends are pointing downwards instead of going upwards. Okay? And I want to write this down because you're going to see it on the homework. And they say it, which one of these do I want to use? I'm going to use this graph. And this is how they talk about end behavior. And you might have seen it before. But they say as x goes to positive infinity, so as x is going this way, f of x, or y, right? F of x is y. What's happening to y? It's going to negative infinity because it's what's happening at the end. And then as x goes to negative infinity, because x can go either positive infinity or negative infinity, then as x goes this way, what happens to y? Well, in this case, y is still going to negative infinity. So you're going to see this in your homework, this notation right here for end behavior, and it's called end behavior. It's what's happening at the end of the graph at infinity. Okay? We want to know what's happening at infinity. And I always just draw this on the graph, and I'll talk about it when we get to the odd degree here, because on even degrees, it's pretty simple, right? It's as x goes this way, what's happening? It's going down on this graph. When x goes this way, what's happening to y? Well, it's going down. Okay? So you can always draw these little arrows, and they will help you. As x goes this way, is it going up or down? Okay, so now I'm going to switch to, why is it the same color? So weird. My odd degree. So now my degree is going to become like x cubed, or x to the 5th, or x to the 7th minus x to the 3rd plus x squared minus 10. Okay, that's just a whole thing. I don't care what's after it. We don't care about what's the rest. The only thing we want to look at, really the only thing we want to look at is this first term. And that first term, the things that we're interested in is the exponent and the leading coefficient, the number that's in front of the x, same as with the even degree. This time my end behavior has something different. So if I have a positive leading coefficient, I want you to write down what you see. I'm just going to go in and draw the arrows in here. Describe what do the graphs have in common? If it's an odd degree and they have a positive leading coefficient. Oh, there's another graph, sorry. Okay. So what do the graphs have in common? And then someone write it in the chat box or tell me here, I don't care. I wonder if we can have one like that on there. Can anyone talk about in the chat what's the pattern, or what do they all have in common? If I have a positive leading coefficient.
Hi, Gumbo.
Hey, take this to the library for me, please. Tell them it's from me.
Okay.
It's the one I borrowed.
What is it?
A charging cord.
Wow, you better get it. I'll be back.
Thanks. Nobody? Okay, so what if I put this on here? What if I did this graph? So here's my axes. And here's a graph that has the same qualities. Okay, it has an odd degree and a positive leading coefficient. The equation for this graph is y equals x. It is a polynomial, even though it's just x. It has positive leading coefficient, which is positive 1. And It's odd degree because it's x to the first power. What can you tell me about that graph? Is there anybody out there? Okay, so this has a positive hope you guys are paying attention because we do have a checkpoint on this on graphing. Okay? If you guys aren't going to participate, I'm just going to go and do it. And then if you have no questions, you have no questions. And if you don't pass the test, you don't pass the test. I mean, that's the mood I'm in. If you guys aren't going to ask questions or answer my questions, then that's what we're going to do. Okay? That's just how it's going to be. So this has a positive slope. If it has an odd degree with a leading coefficient, it's going to start low and go high. It has a positive slope. No matter what's happening in between, notice it's starting low, it's going high, and it has a whole bunch of crap in between. It doesn't matter because it has a positive slope. Starting low, going high. Starting low, going high with a whole bunch of stuff in between. We're going to worry about what all that stuff in between in a little bit. It doesn't have to be exact. It's going to start low and go high. If it has a positive leading coefficient and an odd degree. So what happens if it has a negative slope, negative leading coefficient? If it was y equals negative x, right? So that means it looks like this. The graph starts high and it goes low. So it starts high and it goes low, and it has a whole bunch of stuff in between. Doesn't matter what that stuff is right now. We're just looking at the end behavior. So if I was to write the end behavior of this graph right here, as x goes to positive infinity, so as x goes to positive infinity, f of x is going to negative infinity. And as x goes to negative infinity, so as it goes this way, what's happening to y? Y is going to positive infinity. So my end behavior changes when we start talking about the leading coefficients here. And this will help us sketch out my graphs. If I know if it's an even or odd degree, if I know if it's an even degree, I know my endpoints are going to go in the same direction. If I know if it's an odd degree, I know my endpoints are going in opposite directions. If I know if my leading coefficient's positive or negative, I know if it's negative and it's an even degree that it's going to open downwards, right? So I know just by knowing those two things, I know a lot about what the shape of my graph is going to look like. Okay, so that's why we're doing this. And here we go. Number 1. Which of these graphs could be the graph of f of x equals negative 3x to the 4th and y? So go ahead and write down an answer, a letter, and the reason why you chose it. For this, so it means it's going to be B because it's got a even degree. Oh, that's a lovely way to spell degree. And let's try one more time to erase my lovely spelling error. Let's see, D-E-G-R-E-E. There we go. Even degree and negative.
Thank you, Ms. Campbell.
Thank you. Negative leading coefficient, okay? So that's why it's this one right here. Okay, any questions on that? Does that make sense for those of you who answered?
Yes.
Okay. All right, so This next little chart just kind of talks about how many times it can turn if it's like an x squared. So let's highlight this. This is degree 2, so this would be an x squared one. So I can have one bump. I can have it turn once. If it's degree 2, so this would be x cubed. It can either look like this, the first one here, or it can kind of have some extra little humps in there. Okay, depending on if I have imaginary roots or if I have real roots. So this is what we're going to start talking about, imaginary roots and real roots. Degree 4, I have 2 choices also. I have this little flat one. So notice, I'm going to kind of, let's do this. Here, as I kind of flatten out here, this kind of means I have some imaginary roots. This one I have 1, 2, 3 real roots. Here on this 4th degree, see how it kind of looks like a parabola, but it flattens out down at the bottom. This means I have some imaginary roots. Okay, or I have 1, 2, 3, it crosses the x-axis 4 times. That causes me to have 3 little peaks and valleys, peaks or valleys. Okay, so I've got little 2 valleys and 1 peak because it's opening upwards. So I have 4 x-intercepts. And then we start having variations. As I add more degrees, I start having more variations as we get bigger. So those are just some kind of ideas of what these graphs can kind of look like and what they're going to, how we're going to have to sketch them. Sorry, I'm trying to search for the right words right now today. So I'm not going to spend a lot of time on this graph because I don't think that it's going to help you the most with the graphing. In fact, I know it is not going to help you the most with the graphing. I'm going to go spend time on the stuff that is going to that's going to help us the most. Okay, so so I have this graph. And I want to talk about which equation do you think could be the equation of this graph? So let's talk about the graph and see what we can find out about that we know before we talk about our choices for the equation. So I know that it's opening up and they're in the same, the endpoints, my endpoints are opening in the same direction, right? So this has got to be an even degree, right? And it's got to be a positive leading coefficient because they're opening upwards. So if I have any negative leading coefficients, that's going to make those choices go away immediately, yeah? So that means it can't be A and it can't be C because those have negative leading coefficients. Does that make sense? Right? That makes it pretty easy. And so now I have this choice between B and D. And are they both, now my next question is, do I have an even degree? So let's see, 2, 4, 5. Oh, this has a degree, D has a degree of 5, 2, 3, and B has a degree of 4. So which one would be the right one? B, right? I didn't even have to start looking at the intercepts yet. I just looked at the degree and leading coefficient. Sometimes that's all I need to do to narrow down an equation for a polynomial is know the degree and the leading coefficient. Okay. Other things I could have started looking at. I have a x-intercept at -3. Well, that checks that and that. I have one at +2, checks that and that, and one at 5. So that checked those off. So that was all there, okay? The problem is this one right here, and we're going to talk about that one next, okay? Why this one is not complete. This one doesn't work, but we're going to talk about that right now. Because we could do this problem with just the degree and the leading coefficient. So this part here is going to talk about why that graph really didn't work. And it's the touch versus cross on an x-intercept, okay? So if you can look at these two equations and the graphs just for a minute and kind of study them, and try and decide for yourself what the difference between, sorry, I should make this bigger, what the difference between a touch and a cross is. Sarah, did you get the, see right here, x-intercept, x-intercept. Notice it's just crossing, right? That's a normal parabola. It's just crossing those. Okay, awesome. So what's the difference between that one? And you can look at the equations. They give you the equations too, right? So that at the top it's x plus 6 and x minus 7. And I have an x-intercept at -6 and +7. Great, okay? It went through it. And then at the second one, if you look, I have an x-intercept at, it's like x plus 6 and x minus 7 squared. Here I have 1 at x equals -6. Wow. And I have 2 at x equals 7. I have it twice. So what's the difference between -6 and +7? Well, remember when we were talking about that multiplicity right here, if I was to doing this, instead of writing x equals 7 twice, I would write x equals 7 multiplicity 2, right? So remember when we talked about that? It must have been Thursday, I think, when we talked about it. So what that means when I'm looking at it graphically is that instead of crossing my x-axis, it's going to touch it, or I like to say kiss it because people tend to remember that better. It's just kissing my x-axis and then bouncing back up. Okay, it doesn't cross. It only crosses if it's an odd number, an odd exponent. So let's look over, do they have any? Oh, they don't have any greater than 2, too bad. So if I look at the next one, we're still doing 6 and 7, right? Only this time 6 is the twice and 7 is the 1. Great, it's touching at -6 and crossing at 7. Okay, and here on the last one, if you look, they both have a squared on them. So this would be -6 multiplicity 2, right? And 7 multiplicity 2. And so they both just touching and bouncing back up at those. So if I have this lovely little x minus 7 squared, and I have an answer in the same spot of more than one time, then depending on what this degree is, tells me if I'm going to touch or cross it, okay? So we're going to talk about that now, and that's our multiplicity, okay? Multiplicity is the number of times a given factor appears in the factored form of an equation of a polynomial called multiplicity. The zero associated with this factor, x equals 2, has a multiplicity of 2 because the factor x minus 2 occurs twice. There must be, I wonder where, there must have been an equation somewhere in there. So if I look at this equation, if I look at this graph, this has a multiplicity of 1. How do I know? Because it crossed at all 3 x-intercepts, okay? It crossed the x-axis, has a multiplicity of 1, okay? So if I look at this one, here, is that, see, I can't see. Oh, it helps if I make it bigger. At 4, it had a multiplicity of 1 because it crossed. At 0, it had a multiplicity of 1 because it crossed. But at -4, because it just went up, kissed the x-axis, and came back down, had a multiplicity of 2. Had an even multiplicity. Even multiplicity. Okay? So it touches the x-axis and rebounds back down. So if it has a multiplicity of 4 or 6 or 8 greater than 2, this is kind of what it looks like. And I'm going to draw it on this graph right here that has an even multiplicity. So it would go up like this, and then it would flatten out, and then it would come back down. Okay? So the higher the multiplicity, the more flatter that it's going to be at that point. it's going to look like it's really flat, kind of like, you know how a graph starts at, oh my Lanta, exponential graph starts approaching zero, but it never actually touches zero, but it looks like it is. This graph is actually approaching that point, but it's not really touching it until it gets to the x-axis, and then it starts slowly, that's what it's doing, okay? So it's not really touching it along that whole way, okay? So then we look at odd multiplicity. So what happens if I have a multiplicity of like 3 or 5 or 7? Well, what happens, look at odd multiplicity still crosses. Okay, odd multiplicity crosses because this is an odd, 1 is odd, correct? 1's an odd number, so it goes through the axis. But if it's 3, what happens? Well, what happens at 3 is it has to start flattening out a little bit before it goes through. And if it's 5, it flattens out even more. And if it's 7, it flattens out more. The higher the multiplicity, the wider it flattens out. Okay, so that's what it's kind of look like, and it's really hard to draw. That's why we're just kind of sketching them, you guys. As long as we know where the main points are, and we're going to get to that probably tomorrow. So the max number of x-intercepts I can have for a polynomial is my degree minus 1. Okay, that's the max number of x-intercepts I can have. Does that make sense? Oh, it is not minus 1. It is just my degree. Why did I say my degree minus 1? It's just my degree. Okay? Because if I have a x squared, which is a quadratic, right? Quadratic, I can have 2 x-intercepts. Intercepts. 2 x-intercepts. If I have an x cubed, I can have 3 x-intercepts. If I have x to the 4th, I can have 4. But sometimes those x-intercepts are complex or imaginary. Okay? Even multiplicity touches or kisses. Kisses the axes before going back in the same direction. An odd multiplicity flattens out before crossing. Okay? So odd multiplicity will cross, but it will flatten out. Even multiplicity touches or kisses and goes back in the same direction that it came from, right? So it kind of bounces off. All right, you guys we're doing great. By the way, the last page of these notes we're not going to do, and how are we? Well, we may. How are we doing on time? We're doing pretty good. Okay, so this is a little harder. What is the minimum possible degree for this polynomial? What do you guys think? What's the minimum degree that you guys think we can have? Take into consideration if it touches and bounces back down, that's a minimum of 2, right? If it flattens out, that might be 4. If it flattens out and crosses, that might be 3. So you got to take that stuff into consideration. So what's the minimum possible degree that this polynomial could be? How many x-intercepts do I have? 5. So I have a minimum of 1, 2, 3, 4, 5. So it can be a minimum of the 5th degree. Okay, because it has to have, the degree has to have the number of x-intercepts that's in there. So it can be a minimum of 5. And because it really doesn't have any touches or flatten out or anything, I would be willing to, for myself to say that it's going to be a 5th degree polynomial because it doesn't have any of the other characteristics that we've kind of been talking about. So this is a little harder for you guys. Given that a polynomial of degree is a degree 6, which of the following could be its graph? So first things you want to think about, it's degree 6. So what do we know about an even degree? The what? What do we know about the endpoints of a degree 6? It's an even degree. So what do we know about it?
Both the ends are the same.
Both what?
Both ends point in the same direction.
Yeah, both ends point in the same direction. So if they don't point in the same direction, can it be a 6th degree polynomial? No. So which ones can it not be just right off the bat? By that definition. It cannot be D and it cannot be G because the endpoints do not open in the same direction. Is that okay? Okay, try and find out. I think there's 4 or 5 of them that it can be. Talk about these, and I'm going to work backwards. Is that okay if I start with H and go backwards? I know I didn't make this, so I didn't put them in order that I would talk about them in. So I'm going to start with H. So this is a possibility, right? It goes in, it flattens out and goes through. So I know that's a minimum of 3, right? And so the same thing with this. So this one and this one has a minimum 3. So I can say that would have a minimum of 6 degrees. So I could say that could be 6. It could be 10, depending on how wide I think this flat space is. But I think it's 3. So I'm going to say that it's a possibility of 6. Okay? Is everyone okay with that one? So let's go to F. So I know that this touches and it doesn't look like it's going flat. So I'm going to say that one has 2. And then this one is 1. And this one, look, it's going flat again. So I'm going to say a minimum of 3. And then this one is touching again. So that would have 2. Please, if you don't understand how I'm getting why I think there's that many x-intercepts there, please let me know. So that's 2, 3, 6, 7, 8. So it can't be F because that would have a minimum of 8 x-intercepts. Okay? So E, this would be 1 and 2. But remember from our picture on the last page, if it goes flat, I can have, these are imaginary. We talked about this for really quick, imaginary. So this could be possibly 4 imaginary there. So this could be 6, I would have 2 reals and 4 imaginaries. So E would work for me also because it goes flat at the bottom. And then C here, I have 1 here, 1 here. And again, I have, sorry, let me use a different word for these ones. Instead of imaginary, I'm going to say complex. So 4 complex here. So 4 complex. There's not a lot of difference between complex and imaginary. But I'm going to say complex instead of imaginary. So again here, I think because this flattens out and touches and goes back down, we know it's an even number. We know it's not 2 because it just doesn't touch and bounce back down. So it's got to be greater than 2. So I can say that I can believe that this would be 4 here, and then 5 and 6. So I'm going to say that's C also. So I always in the past, I always said that A, I would say no on A. I'm just going to say this. Because to me, it looks like just a regular parabola. It doesn't flatten out. But Mr. Call talked me into saying that, okay, he convinced me that possibly A could be 6 also. So again, here's 1 and 1. And then it does kind of go flat down here, right? And it could just be the computer rendering of it, or it could just be so small that we can't see that it's gone flat. Okay? So there's a possibility that that could also be 4 and that could be A also. I just leave a question mark next to A because some people say A and some people don't. Okay, if you can convince me that you think A has 6, then great. Okay, I still don't think it is, but Mr. Call does, and so great. Awesome. Okay, so I said A, C, E, and H. Are we okay with that? So what we're going to do for I'm going to talk about how to find the rest of these, because basically for your homework today, you have to find all this stuff from an equation, and that's it. It's pretty easy. We already know how to find an x-intercept, right? You set them equal to 0 and solve, right? We've done that. How would I find a y-intercept, though? If I have this, do I have an equation on this page? I don't have an equation on this page. Let me write one down. If I have an equation, let's go back to, ooh, I don't like that equation. I'm just going to write one down. If I have y equals x minus 5 times x plus 3 squared times x minus 4. How would I find the y-intercept? Anybody know? Because I want to make sure that you guys know how to do it. I know you know how to do it. I just don't know if you remember how to do it. Does that make sense? Okay, so I just want to talk about finding the x-intercept, because we've talked about how to find the x-intercepts. We talked about how to find the leading coefficient, how to find the degree. We're not going to talk about plotting points until next class period. That's almost all the next class period, okay? So how do I find a y-intercept? So if I have, oh, I don't need to draw a graph, it's right here. This is a y-intercept, right? Anywhere on this axis is a y-intercept, right? Can you tell me the location of that point? I'll just draw it up. I'll just make it big. Can you tell me the location of that point? Do I need to make it bigger?
Is it on 7?
Yeah, it is. Good. So this point is what? 0, 7. Beautiful. What is the location of this point?
The one that you just put
Yeah, this new one right here.
0, -1.
0, -1. Gorgeous. What about this one? This one right here.
0, 3.
0, 3. What do all three of those have in common?
They're on the line 0.
Yeah, all the x value is always what?
0.
0. So if I have my y-intercept, right? X always equals what? 0. Doesn't matter. Doesn't matter where I'm at on that y-axis. X always equals 0. Does that make sense? So how do I find my y-intercept here? Guess what I'm going to do? I'm going to set x equal to 0 and solve. And that's your y-intercept. So I would get 0 minus 5 times 0 plus 3 squared times 0 minus 4. So that's going to be negative 5 times 3 squared times negative 4, or 9 times 20, or 180. So that would be my y-intercept. Does that make sense? All I do is plug that x in for 0 and then do order of operations. That gives you your y-intercept. Now, I'm going to tell you the truth. If I was graphing this, is there any way I'd put, is there any way there'd be a negative? Wait, is not negative? No, because a negative times a negative is a positive. Oh. No, that one was a positive 3. Sorry, Jess. I was on the wrong, that point on the graph was a positive 3. Are you okay with that? Okay. There's no way I'd have a negative 180 on my graph. So when we talk about graphing this, sometimes my y-intercept is not on my graph, and we'll talk about that tomorrow. What we do in that case, like that wouldn't be on the graph. But we'd still sketch it, okay? So on your Delta Math, you're not going to be graphing yet. You're just going to be finding all this information. So if you guys will go ahead and start doing that, that would be awesome. You guys are awesome. Okay, and you have about 20 minutes. You should be able to get it done.